Hello. Just so I know who I'm talking to, raise your hands who knows what computer vision is, who's used OpenCV, who writes Python, who's worked with TensorFlow,
Heard of it.
who knows what a neural net is. Awesome. Okay, so so we do a lot of computer vision, and because it's really cool, we want to live in the future, and that doesn't pay the bills though. So we also do computer vision to just automate things, to replace human beings where we can, so Rosie the robot. So in 2010, there's this competition called ImageNet. It started out just being a database of images, and the competition became so you can autonomously classify those images. And so this really kicked off. Neural net's been around for a long time. AI's been around for a long time. Computer vision's been around for a long time, but it just recently got hot. It recently got good. Is another way to say it. And the difference between when it wasn't good and when it was good is money. Is that there was suddenly money in this, and you can begin to see in 2011, 2012, the winners of these competitions would leave school and go to Google, or leave school and go to Microsoft, and leave school and go where, and then they start to partner. So Google won a lot of early competitions. Microsoft won a couple with their CTA toolkit. But the reason why things got better was because we put money into it, we put time into it, resources into it, and the neural nets got better fast. So that was the difference. So we talk about, we want to live in the future, so we build cool things like that air hockey robot using computer vision, and we'll kind of show that and talk about that. Tim built that. But the reality is that we've been wanting to live in the future for a long time. Jetsons is an old cartoon. That doesn't actually move us forward. When you can attach some money to it and put a profit incentive, that's how things like this move forward. So the way that it moved forward, the number one reason why AI moved forward, computer vision moved forward, starting about 2010, 2011, 2012, is that Google found a way to incentivize movement by classifying images. So everybody remembers they bought YouTube for over $1 billion, and people thought they were foolish. This company loses money every month. How are you going to do something with this? Two things they did. One, they also at the same time started up a 411 service, an information service. They're in San Francisco. You dial 411, and just Google just bought an information service. And they started training their neurons that were able to listen to audio, listen to people, and know what it is they wanted. And it had a commercial aspect because you dialed for one because you wanted to go somewhere and buy something. And then the second thing they did is they started competing in these ImageNet competitions. And the whole idea was that they were going to take frames of those YouTube videos, right, and then attempt to classify those frames so they can sell you better ads. Because if you're looking at a video and we grab a frame off, I see it's a cat, I can advertise cat food to you, and you're more likely to buy the cat food from the advertisement. And so they make more money. And that was it. That was all it was, is that if they can increase the odds of you clicking through the ad, then they can make more money. But that was enough to put billions of dollars into computer vision and AI, and that's the real reason we're standing here talking about it right now. So the first problem of computer vision, the first thing we want to solve is classification. I've got an image, I have some thing, and I want to know what it is, so I want to classify it. The second problem is localization. And localization just falls right out of classification, because once you have something that can look at an image or a rectangle and say, yes, this is a cat, well then you just have that frame be smaller than the image, and you drag that frame across the picture. And in all the spots where you classify a cat, it's true, and every spot where you didn't, it's not true, you draw a rectangle around it, and there you go, you've got localization. So it just fell out. It was almost on accident. We didn't, nobody was working towards that necessarily. And then you're one step away from there from detection. So in 2014, we had the first really good detection, and we brought that with us today. So this is Google's inception model, and it's looking at all of you. But if you've got, you see this? You're wearing a t-shirt. Oh, you're a punching bag. That's how good this is. Water bottle, that's pretty good. Rubber what? What is that? Rubber something? Rubber eraser, that's fantastic. So, that was great, right? We can do...
Just classify this as a movie theater.
That's not bad. That's not terrible, honestly. So, again, if it's driving advertising dollars, then it's driving investment, it's hiring people, and it's putting people on teams looking to improve that. After we have detection, then we have segmentation. Segmentation is necessary for autonomous cars. They want to know where the other cars move around. It's good that you can classify it, good that you can localize, but let me do segmentation. But mostly what it's been good for in the last few years is for Snapchat filters. It identifies where your face is and then it overlays and does some cute stuff. We've used segmentation and we do some kind of cute tricks with camera. We make the problem easier, and instead of doing segmentation on full color images, we'll do edge detection first before we do the segmentation, before we do anything else, and then we'll extract data from that. It turns out edges are a lot easier to work with than full images, and so. Add all those up, and you have a self-driving car. Looking at the world around you in a different way. So that's, just from a high level, what those problems are. So, Facebook has asked you to confirm, it identifies you in the picture. Yes, I assume nobody in this room uses Facebook, but your mother has been asked by Facebook many times to say, is this you in the picture? What you're doing is you are providing training data for Facebook so that they can identify your mother and any other picture that somebody else takes that picture. And you'd think, oh, this is pretty nefarious, and you'd be right, it's pretty nefarious, but that's not what we're here to talk about. But here we are looking close to the phone card. But what I did want to talk about today, because I think it's kind of interesting, the kind of one real concept I wanted to talk about was, how does this work? How does that work? And it seems like we had some, not everybody's a TensorFlow expert, so we'll talk about that. And why is it so good now? So before we can get that, we need to kind of talk about what an image is. I'm going to do some coding. I'm going to put some live code up. Hands up, who's used Jupyter? Nobody? Awesome. I'll help you. So maybe I should. My tongue keeps sitting that pad. So we do. So we've talked about OpenCV. There's other libraries out there that we use pretty commonly. One is Scikit-Image. It's not important what libraries we use. The tools we use are pretty important. We use Python primarily to do computer vision. The reason we use Python is because it's so good at manipulating matrices of numbers. It's a mathematical language. The purpose of any language is so that you as a programmer can express yourself succinctly and get the software to do do your bidding. You've got some model in your head, you want to make that model happen in code. So picking the right tool for the job is great. Every serious person doing computer vision is doing it in Python. There are people doing R and some other languages. Primarily Python's the language. Again, and I'm going to show you why that is. It's fantastic at manipulating matrices and numbers. So this app here is a web-based app. It's called Jupyter Notebook. You can do inline markdown and code, which is fantastic, and you can execute that code. So I just kind of prepared a load of code we're going to run here. So I initialized some libraries, and I've set this matrix A and filled it up with zeros. It's a 5x5 matrix. You can see that it's 5x5 matrix of zeros. Just as a point of reference, we'll be doing a shape later. You can see it's 5x5. I'm going to fill up the center with ones. You can already see, like, if you're writing this in C# or JavaScript or something else, and you wanted to just zero out an array of, a matrix like that, 5x5 matrix, and then set the middle values to 1. It's a little bit less difficult than this, but it's a one-line expression, and there you go. And so here's the matrix, much of zeros and ones in it, but let's display it as an image, because after all, that's all images are. If you're looking at a 320 by 240 pixel image, what you're really looking at is a matrix, 320 by 240, and at each value in a black and white image, it's either off or on, right? The pixel either is on or it's off. If it's a grayscale image, it's got some variation between black and white, then it's still 320 by 240 pixels, it's a matrix. But each value, instead of being a 0 or a 1, is a number between 0 and 255, right, for how black or how white it is. If you're looking at a color image, who knows what kind of matrix that looks like? It's got 3 layers, right? What are those 3 layers? Red, green, and blue. You took a t-shirt? You have a t-shirt. After the show, come get a t-shirt. So I took the same matrix we were looking at. I set the center to 0 because, it's a pretty pattern. And we'll show that picture. There we are. So really, really simple, right? Each one of those is a pixel. You can see, 0, 0, all the way across, all the way down. They're just really simple. We're going to resize this because it's not very cool. And there's that same picture, but resized to 100 by 100. Same thing, right? Just ones and zeros. The new shape of this thing, 100 by 100. That's nice black and white. It's actually grayscale, but now we're going to do one with 3 layers. Now, as I look at it, this is again a 5x5. But I'm a human being, and this 5x5 doesn't look like 5x5, it looks like 5x3, but it is 5x5. So we're just going to transpose, well, first we'll look at one of those fields. At x, y coordinate 0, we have value of 0 right now. But I'm going to swap the axes, because I'm a human being, that's the way that I look at matrices. And that looks a little more clear, right? Red, green, blue right there, with your 5x5. Same 5x5. All right? So we're going to do the same thing. We didn't, well, somewhat the same thing. I'm going to put the entire face full red, all 55s. I'm going to set the center to zeros there and put 255 on the green layer. Yeah, something like that. And then on the blue layer is going to be with that dot in the center. Right. So conceptually, and again, I'm sorry this is way below your skill level, heads, but conceptually getting to understand how computer vision works and why it works so well today, it's kind of important to know that it works so well because photos are just a bunch of numbers. They're really, and it's not out of reach for anybody to interact with the images on that level. So let's take something real just so you can kind of see that this is still true.
I'm not quite sure what you're doing on the resizing. Are you just making it from 5x5 to 100 by 100 and it's just...
Yeah, and we're doing
It's got a range in between, so it's not just hard.
Yeah, there's 101 libraries out there for doing image resizing. If we had just resized the array without changing the shape at all, you'd have a teeny tiny pixel in the middle, and
right.
you'll be able to see it if you, we just decided to stretch it.
Okay, just want to make sure.
All right, so I've loaded up the strawberries JPEG, and here's what it looks like. Nice big fat image, 1400 by 2100 pixels. We're going to resize that down to make it usable. I'm going to draw a little rectangle. I'm going to take that little section out because it's too much data to show you and be reasonable. There's that one little rectangle, and there you go. There's the RGB. But it's just sort of the, kind of top to bottom conceptually that, every photograph, every image, every whatever. It's just, that's how we're going to interact with it. That's why this is, so, making that connection between we as human beings looking at a picture, looking at, through our eyes, and what can you do with that mathematically? We need to transform a computer vision problem from being a, photographic problem to being a math problem. How do we do that? Well, this is conceptually an important place to start, is that every photo is just a matrix of numbers. So, everybody's seen one of these. I'm just going to deal with the layout. We don't do console-based presentations. Everybody's seen, raise your hand. Have you seen one of these neural network diagrams like this? These are awful. I mean, they're not. They don't explain a whole lot. They're never. They always say hidden layer 1, 2, 3, which doesn't tell you anything about what's really going on the inside. But the input layer is a photograph, and the output layer is it a cat? Is it a dog? Is it something? And then there's magic in between. And so conceptually, I just wanted to simplify this and make this something that's accessible, because it's not that hard. And so what I want you to think about is think about a Plinko board. And think about the fact that you're making a Plinko board. So you've got this piece of wood, pegs, and each peg has some properties of that peg, which when the Plinko hits that peg, it's either going to right or left to the next peg, and then right or left to the next peg, right? And so we start out by dropping an image at the top. The image is your Plinko, and it hits the first neuron in your neural network, and it either goes right or left based on the properties of the peg and the properties of that image. And then on the next peg, again and again and again. And in a deep neural network, you hear people talk about deep learning, there might be 100 layers there. And in each layer, there might be 1,000 nodes across. But at the end of the day, this is all that's happening, is that your picture of a cat is hitting these Plinko pegs and eventually falls into the cat bucket at the bottom. All right? So if you look at one of those Plinko pegs, you got input data coming in. There are weights associated with that peg. They're called weights that determine whether or not you make it to the next peg. You put those things together, you start to come up with that picture of things. So we talked about the image is just a bunch of numbers. This is a demonstration of how we'll transform your large image of cat, there's 1,000 pixels by 1,000 pixels, into a single binary, is this a cat or not a cat? At parts of that neural network, we need to reduce the problem. We need to reduce that picture, because 1,000 by 1,000 is too many. It's not a single Boolean yes or no. And part of that reduction is to try to capture the essence of what's in the picture, but in a smaller matrix. And so what we'll do is it's called convolving. Convolving is to drag this frame across your image and run, really, it's just a little bit of math. To take those 9 values at one of those filters and do matrix multiplication and come up with just one value. And so you're shrinking the image without losing the features in the image. And the math's not that hard. But you don't need to do it. But it's nice to know what it's doing. So if the right side is your filter and the left side is your actual RGB value, 2 times 0 plus 10 times -1 plus 60 times 1, and you come up with a single number. So now those 9 numbers get turned into one number, but it captures some essence of those previous 9 numbers. The result of that ends up being this I'm gonna walk over. So it's hard to see, but there's only 9 buckets here. Well, I can't see anybody, but there's 9 buckets here. And there's an input image. It's the same input image all across. And you think about this as the Plinko board. This is the first row of pegs on that Plinko board. But it's It's a whole matrix of ones and zeros, in this case, of black or white pixels on that floor. As it falls through, when you first start out in a neural network, it's all a bunch of snow. It looks like a television set that's scrambled up. It's just random noise. But as you train this neural network, it begins to take some shape, and you start to see some things fall through. But at the end, once it's done training, you run this thing. This image falls to this filter, and there's only one value at the end. This is the fourth bucket. Actually, the fifth bucket, zero. This is what that neural network is visualized. So the inception model we showed a little bit ago, if you break that down and visualize its layers, it looks like this. This is from the inception model. And this is faces, cars, elephants, and chairs. So if we pointed at an elephant, we get an elephant.
No hot dogs?
No hot dogs. At the lowest, at the first levels, what you see are just edges, just lines, not real features. And in with the four picture there, as you get deeper and deeper in that neural network, they start taking shape. They start looking like real faces. And so, you start capturing style. You capturing in edges. You start capturing features, and that's. It's got some really interesting implications, especially when it breaks down and pulls out styles, for example. Raise your hand if you've seen the thing where they do a style transfer, where you've got a famous painting like Monet's Water Lilies, and you take a picture of your kids, and they combine them together. So what they're doing there is they've taken this inception model, where, again, there's multiple layers of this neural network, and it starts capturing styles at one layer and capturing content in another. And we end up optimizing taking a picture of your kids or whatever it is, and morphing that picture until it matches the style, until that neural network identifies it as being from that painting. Let's go ahead and run the more back. Just run your own camera. So, yeah, you want to turn around? So this is a famous painting called Mosaic. And what we're doing here is we're taking the webcam, we're capturing a frame off the webcam, and we're adding noise and morphing that image so that it starts triggering the trained neural network that has been trained to identify that mosaic image. And we're able to do that fast enough that we can actually generate this new image. Let's do the
CPU getting hot right now.
It's using the GPU for this.
Yeah. Yeah, this is, we're,
CUDA? CUDA?
yeah. We did a couple others. This is pretty great, actually.
And with the 80s rock stars, what do you do with that?
Oh yeah, this would be a good aha for sure. So we're painting again. We're essentially creating a painting, and this is all programmatic, which is pretty cool.
Just frame it out.
Yeah, I mean, this is somewhere around 25 frames a second at this point, but it's not bad.
Yeah, this isn't a 1080. So
No.
We tried doing like stereo patches earlier, like an Oculus or something like that, and try to do like an overlay head, or overlay, I'm sorry, the
Of this?
Yeah.
No, this is almost entirely to show off. It's like a lot like the air hockey bug. There's no practical application for that. There's no, we're just showing off. So we did an AI summit in St. Louis, September 17th, so, well, here, we'll get to the rest of these things. You know, the real applications are identifying what is benign versus malignant breast cancer, right? Is it just ones and zeros? It's just numbers. So we can train a neural network to identify, just like your face, just like your cat, to start to identify cancer, and that's a good thing. So, and this is already in use. This isn't our code, but I've been, reading about this for years. This is actually one of the things that inspired me to get into computer vision, although I did AI back in college, is that lives are being saved. So there's two types of machine learning. There's unsupervised and supervised machine learning. Supervised is that you have, it's like having 1,000 pictures of a cat and it says the word cat, 1,000 pictures of a dog, it says the word dog, and you can train it. It's supervised. It's pre-labeled. And then there's unsupervised, where you have no idea what you're looking at, and that's all of this data. It's one way to look at all this data. You can look at more of this breast cancer data to do that. And so what I'm told is that oncologists had 6 or 7 markers they would look for in these images of the mammograms. Or it's not mammogram, that's a biopsy, stained biopsy. And they set unsupervised learning, machine learning, to try to replicate that and detect it and come up with its own sort of groupings and classification to identify unknown parts. After they let this thing run for a weekend, it came back and showed all 6 or 7 of those markers, and then 3 or 4 more markers that hadn't been known about before. Today, they're using all 10 or 11 markers. The oncologists just, with their eyes, so that's pretty neat. That's pretty good.
They were like, oh yeah, those are markers.
Yeah.
That's great.
Yeah, we use really, really simple stuff. I don't know if you can tell here, but the top frame came with a webcam frame, just 4 pictures right after each other. We enhanced the colors a little bit. We can tell you what your heartbeat is while you're doing it live in camera. That's pretty slick. Here's a really cool one. So this has got freaking lasers on it. And so it uses computer vision to, again, pull off of a webcam. It looks at a mosquito and it figures out whether it's a male or female. And if it's female, lasers. If it's male, no lasers. And so what it ends up being is a wall that only it's a filter that only lets males
That's
through.
the best bug zapper I've ever heard of.
Yeah.
That's a-
Well, I mean, if you've got malaria and you're worried about spreading malaria, you just kill all the women and then you're done. That's pretty much. I don't want to be chauvinist. I'm just in a mosquito population. I'm sorry. In a mosquito population, that's how you do it, right? You kill the women and then you don't have more children that are spreading that malaria. So that's pretty slick. Yeah. So we do some more again. And this, just as an aside, I really like this. You saw the object detection. We've been watching some other people intentionally print up things that look to a human being, like a turtle, for example. This is a 3D print. But it's classified as a rifle. So if you were to walk through an airport with this turtle and they're using this object detection, so this is called adversarially perturbed, which is like, you can tell like one of us made up that term. It's fantastic to take an object, and so and there's all sorts of examples of this, but it looks to us like a turtle, but this is triggering, in that neural network, all the rifle. Yeah.
So does a normal turtle register as a rifle?
No. Normal turtle all day long is a turtle, but this one has been painted on purpose. Not painted, but that's a print on purpose, so that print of a skin. Have you seen people that do with makeup and they'll paint eyes on themselves, and they're just trying to fool the face detection systems? That's what this is. So it's intentionally perturbed.
But how does it, has anyone researched how that looks like a rifle to a...
Yeah.
They probably made it because they knew how it worked. They hacked it.
They reverse engineered, the specific.
Well, you come back. So you got this right? So if you know that frame off the camera, you want it to fall into the elephant category, even though it's a chair. Forget about the edges. You're going to, and it's too obvious to human beings. You don't want to be sure of that. So you're going to start painting these patterns on it, but in a subtle way that a human being wouldn't pick up. And so that you'll get enough things fall through the edges. Everything's going to fall through the edges. You're going to get some percentage of your turtle images are going to, or chair images are going to fall through the first layer. But you want to make it to that last layer to be identified as an elephant. So there are things that we wouldn't identify as an elephant, but they were specifically designed for this neural network. And the reason that works is because, and this only works on the inception model, is if you publish your model. And Google, everybody's publishing their models now. So you can go download, and it's a 300 meg file, this model, and go look at it, and then go intentionally perturb some other object to fit this model.
So do you in the future have to worry about people socially engineering AI?
Oh yeah. Oh no, not future, right now.
Right now?
Yeah, right now. No, if you don't think that next week I'm going to have one of these printed up,
Oh, yeah.
I'm going to hand them to people to go to the airport. No, not the airport.
All right, have you seen the clothes that they're selling now already with like eye faces on them?
Yeah.
That's
This
This is our
Well, and then you make rifles that look like turtles, right?
Yeah, you can do that. You can actually do that. You totally can do that. But we were going to go there. It's kind of dark. It's kind of dark. So there are certain breeds of dogs that are really hard to tell apart from a blueberry muffin. So same deal. The same kinds of things pop up.
I can just imagine at a political event having a whole bunch of protesters wearing makeup that'll make trigger the same person, so they end up throwing out the data. You know?
Yeah. Well, I didn't want to take up all the time. I want you guys to be able to ask. Have you had a chance to see the air hockey table about that we brought with us? So for people that didn't, it's in back, and we'll set it up again. But this guy Tim built this. So I said to Tim, because we were on this show, AI Summit, and this was September 17th of the show. I think somewhere around August 14th, I said to Tim, can you build something cool? How about and then we talked about a foosball table, which is ridiculous because it's too many motors and everything else. And so we settled on this air hockey table. And in a month, he built this thing. And most of it's really the hardware. Essentially, it's an air hockey table. His kid's air hockey table, all the time, right? Was essentially a 2D plot printer put on top of it, and then we got a webcam pointed down from the laptop, controlling the servos on the 2D plot printer. And so you can, it's a V1. It's not great. But it's going to be great. You can tell it's going to be great. It's still fun to play against. It feels like you're playing against a 7-year-old. By the time we soup this thing up, I mean, V2, V3 next year, you're not going to be able to beat it. So if you played it and have any questions, Tim's your man.
Can you put your contact info back up on the screen?
I don't think I have my contact info up. Last time I was at one of these conventions, we didn't put contact info up. Any questions?
So when you're training the program, for instance, I'm assuming it's using just a normal image to recognize that turtle as a rifle. If they ran it through like an IR, would it also recognize it? Or do you have to use like a specific format that you train it against?
So they've already trained their neural network.
Right.
So again, when you first have a neural network, it looks like garbage. You just fill it with a bunch of noise, and then you start sending through. So the Plinko board, you start dropping a new image through. It gets to the bottom, and it says, oh, that's an elephant, and it really was a rifle or whatever. So then you back propagate the fact that it was a rifle, not an elephant, back through your neural network, and if you do that enough times, you get 100,000 times, so it starts looking like something. It starts capturing something about the image to make it fall into that category. You're correcting it later. Now, the Google Inception model is interesting because it's connected at certain layers, and what fell out of that was that style was getting captured at one layer, and content artifacts were getting captured at another layer. So they published it, like everybody publishes everything, and then that's what people said. Well, hold on a second. What if we could trigger, we could trigger through printing that we fall into the wrong category? So it only works on an already trained network that's been published out there. But for something like Inception, it's everywhere, right? So we pulled it down in 20 minutes and started running it, and we literally put the machine together on the drive down here. So Tim re-imaged this machine before we came down. So it really wasn't much to get. The hardest part was getting OpenCV and everything installed on it, really not grabbing the code.
It's slow on a 4G network.
Did your question, or?
Yeah, so for like really specific stuff, like Samsung and Apple's like Face ID and stuff like that, I guess they train it. I guess unpublished they wouldn't know how to do stuff.
Yeah, well, I mean, Microsoft, did you just say Microsoft? Is that what you said?
Just like Android and iOS.
Oh.
Facial recognition now to unlock phones and things like that. But they said
They're not publishing that, right? So facial recognition is a little bit of a different, right? Because how can it train on your image over and over again? So they're not using neural nets to do that. They're not training neural nets to recognize your face. Although that would be better.
that's what they said for the Apple one. There's neural nets to train their AI to
No,
recognize
it's
you.
not possible. It's completely impossible to recognize your face. Because you didn't submit 1,000 samples of your face to Apple. Or maybe you did.
You are when you're using their phone, I guarantee.
But when you first buy it and you first
Well,
unlock
not
it,
at first, right.
there's no way that it's been trained to do that. Now, what I do believe is it's probably been trained to measure the distance between your pupils and to find your pupil. That's a trivial problem, just to find key points on your face, no matter which way you're looking at it, to measure the distances and use that initially as a way to unlock the phone. And that probably works well enough until it gathers more data.
And you don't need a neural network for that. You can just use OpenCV.
Oh my God, clever math will get you so far.
I've read that one issue with training is that with neural net or image recognition, it may be picking out on other bits in the image other than what you're intending
Yeah.
training for, and recognizing that. You know, if all you're trying to training how to tell a wolf from a lion, and all your wolf pictures are have a green green background on
Yep.
the lion pictures that have background graphs, then it may be picking up on the different
So
background.
the question is that, or the comment is that depending on the data you train it with, you may be keying off the wrong feature. So again, if you have all of your pictures of giraffes happen to have the green ball in it that's in the giraffe cage at the zoo, and then you think you're doing a great job identifying giraffes, but the next time you put a picture of a lion with a green ball in it, you go, oh, that's a giraffe. So that's called overfitting. That's a huge problem in neural networks and training neural networks. It's called overfitting, which is to say that you've trained your neural network to be really good at doing prediction based on your data set. And if your data was not, clean, right? It had a picture of a green ball or something, and that's why you see some, a lot of these sort of pictures like this cat is it's very isolated of the cat, but it's probably picking up grass as well. That becomes a feature that gets trained in, and so you want cats not on grass. You want cats in various places, on cars and in hot balloons. I don't know what I'm saying, but
Yeah, I read about the one about coyotes and wolves, and it was picking up in the snow.
Yeah.
Versus, who was it? It was like Google's, that was like a story.
yeah, it's really, when you look at the image net, right? It's because those are all individual images. Oh, and by the way, they're tiny. I mean, you think, oh, I'm training on this big 300 pixel. No. They're all like 28 pixels by 28 pixels or 32 pixels. They're tiny, so what you're actually getting on there is nothing. And that's because, well, we're lazy and we like to, we act like there's, this great revolution of technology that's just happened, and it's not. We got,
enough GPU to pick.
yeah, that's, so, absolutely.
What do you think about the Intel's neural net on a stick platform?
A neural net on a stick?
Yeah, they're making like a specific hardware for it. It's like a USB dongle.
I think Intel is desperate to get back in the game. NVIDIA owns it right now.
NVIDIA owns it, yeah.
And I don't take anybody seriously that, so if you it's in an earlier talk yesterday about something else, and so go find the people that are amazing at the thing and figure out what they're doing and what they're doing. The top 20 people doing computer vision or AI neural nets in the world, I mean, they're all doing TensorFlow. They're all doing, they're using NVIDIA and CUDA. So you don't fight a problem you don't need to fight. Don't fight a battle you don't need to fight. Go use what the best people are using, at least initially, until you feel like you need to go veer off and make your own path. But no.
NVIDIA has a small graphic card designed for tiny projects that it's about the size of a credit card, and I would trust that one over a flash drive size.
Awesome, thank you.
Well, when do you need tiny processing anyway? So most of the work is in training the neural network, not running the neural network. Think of the Plinko board. Most of the work is training your Plinko board so you've got all the right weights on those pegs. To actually run the Plinko board is nothing. Just drop the Plinko through there. There's no real processing required to run the neural network. All the processing is required to train the neural network. So you're moving compute. 20 years ago, we would do all the computation when we get the image. There's no way you could do real-time anything because there's too much math involved in dealing with that image. Today, we do most of our compute ahead of time training this neural network. Then when you actually run it, there's no real CPU. Almost nothing is being done to just say, is this a cat or not? It's all the training of the network.
That's why some companies are making their model where they train data and then they sell the trained data to other companies so that they can just run it on that trained data.
Yeah. So doing your work on a desktop with a NVIDIA 1080 Ti is a fantastic card and it's relatively inexpensive. Yeah, it'll be fast. Other questions?
Can you talk about any projects that you've done for clients?
Yeah, well, the coolest project we've done, I can't talk about, but I can talk about in general terms. And it's only because they're going to go out and sell this to their customers. But there is a company that deals in currency, and counterfeiting is a big problem. And it's a global company that does global currency. And so we built software that if you have that currency, that coin or bill or whatever it is, with computer vision, we can, within 3 seconds, tell you if they've ever seen that coin before, right? And so if you think about the way that a human being, a numismatist, would look at a coin, they're looking at features on the coin, they're looking at scratches and dents and colors. Numismatist, that is somebody who specializes in coins, for example.
A coin collector.
Coin collector. So when they look at coin, they don't look at it like a photograph. Like if you were doing a 10i reverse image search, you're looking at the photograph, how similar is this photograph to another photograph, right? But you're going to miss if the coin is rotated, if the coin is at an angle, if there's different lighting, you're going to miss. A human being doesn't miss that. They don't even notice that. They're just looking for those features. In fact, and they can, look at what features should be there versus what shouldn't be there. And so that's what we wrote for them, is that same sort of thing to say, we can identify counterfeit coins, we can identify if you've seen this coin or bill previously. But that's pretty wicked cool. Yeah.
What is the time factor versus resolution and accuracy? Have you looked at any of those? Sounds like you're dealing with a rock curve here.
Yeah, so, again, ImageNet is a pretty small image. It's not even 320 by 240. The smaller the image, the better. Even if you have large images, you're downsampling them to make them computable in a reasonable amount of time, right? Because I don't want to start and wait for 2 weeks for something to compute in my lab, and I'm not going to go give Amazon $3,000 to compute it, in 2 days in their labs. So it turns out that being clever is a lot better than having a lot of money. And so if you, again, so I showed earlier the real-time edge detection, right? We use that to cheat a lot because when you could take, again, a full color, large resolution image, cheat a little by shrinking it down a little bit, doing a Gaussian blur up because you really only care about where something is, generally speaking, do edge detection. Now you're just doing black and white, just zeros and ones. Oh my God, now suddenly your 4 meg PNG file right from a single frame turned into, I don't know, less than 100 kilobytes, right? And maybe if you're lucky, it's less than 100 bytes by the time you're done with it. Now we can go do some math on it. Now we can go send that through neural networks and do training. So the first instinct for most people is to throw more horsepower at it. That is the wrong instinct. Be clever first. So I was very, very lucky that I grew up in the days of floppy disks, and you had 720K to store all of your data, and you couldn't go over. There's no, you could punch a hole and then flip the disk over, get another 720, right? Or it was 360, total of 720. That forced us, it's the famous quote from Bill Gates, why would anybody need more than 64K of memory or something like that, right? That people that grew up in that kind of like, you tell your kids, you don't know what it was like, we walked uphill both ways. Some new programmer is talking about, like, you have no idea how good you have it, but I feel so lucky that I went through that because every problem we look at, we don't think, well, let's just throw some more CPU at it or some more GPU at it. How can we rethink this problem and make it a simpler problem? And, you know, Edges is really slick. Like, that's totally, nobody talks about that, but that's a really slick way of you think about the cat, of just looking at the edges only, you get just as much data out of that.
But is there a time function for determination against some trust factor or accuracy that it is a cat? Size versus time versus accuracy, has that work been done yet?
I'm not aware of it. You know, it's not just cat at this point, right? It's the classification for all kinds of cats, tabby cats and male cats and female cats and cats in here and cats in there, and there's multiple cats versus one cat and young cat versus old cat. There's a whole lot of classification. When you think about the problem of detection, right? What is in this image? It's a cow, dog, whatever. It's not one neural net that says, oh, there's a cow and a dog and a ball. It's 1,000 neural nets. It's one neural net that's looking for a golf ball, one neural net's looking for a tractor, one neural net's looking for a cow, one neural net's looking for a cat, or maybe specific kinds of cats. But you run all 1,000 of those neural nets at the same time on the same image on 1,000 virtual machines. Now you've got, in real time, that's why Google's Google, right? So the trick is not, let's build some really complex single neural network that can do everything at once. It's just to do one thing. And so there's not just a cat, but there's a tabby cat and an adult cat. And so in that sense, they do throw money at it. Yes, sir.
So if you're building a system that needs to be able to recognize a number of different things, does each of the patterns require different neural nets? So you basically have to keep switching context to try out possible matches one at a time.
Well, this is where I kind of come back to being clever. You simplify your problem. You don't throw a whole image of a baseball card at a single neural net. You do edge detection first, and you look specifically for certain parts of the card that are different and that are unexpected, unexpected features. And you isolate your problem down to a smaller subset. And now I've got a known set of classes, right? I'm looking for, if I'm trying to classify, for example, I've got a known set of cards I can classify it as. So I simplify the problem, I isolate the region I'm really looking for, identifying markers, and I've got a known set of classes. So we're back to supervised learning. I've got some pre-labeled data, now I can do a neural net, but I'm not doing a neural net on the whole baseball card. I'm doing a neural net on just a couple of different corners of the baseball card. So, being clever. Well, thank you.